Welcome, class. Today we'll be discussing briefly the periodic table and the atomic structure. At the end of this PowerPoint, you will be able to state and describe the parts of the atom, explain the relationship between protons, neutrons, and electrons, define isotope, interpret different elemental expressions, calculate average atomic mass, explain the basic setup of the periodic table. We go into more detail in Unit 4, I believe. And lastly, you're going to differentiate between metals, nonmetals, and metalloids. Let's take a brief look at the modern view of the atomic structure. There's three main particles we're going to be discussing: protons, neutrons, and electrons. The electrons are negative and they're responsible for chemical behavior. They are found outside of the nucleus. The protons and neutrons make up the nucleus. The protons are positive, the neutrons have no charge. In order for an atom to be neutral, the number of protons needs to equal the number of electrons. And this should make sense to you. In order to be neutral, you don't want there to be a charge. So the number of positives needs to equal the number of negatives. The nucleus is very small, it's very positive, and it's very dense. It does not take up much space. So most of the atom is actually empty space, and that's where we find the electrons. Between the nucleus, which is positive, and the electrons, which is negative, we find different electrostatic forces, static electricity kind of. And we call this Coulomb's law. Now you're not going to find this in your textbook, but you will find it in a physics book. Coulomb's law basically states that opposites attract, like charges repel, and distance affects them. The closer two particles are, the more the force is going to be. The farther apart, the less it's going to be. The mass of one atom has a label of AMU, atomic mass unit. Now you guys remember from last year, we often found the mass of an atom, and usually we wrote that in grams because we were talking about 1 mole, not just one atom. And in the mass, we do not include the electron because they are so incredibly small. The mass is only made up of protons and neutrons. The electron would be like if you were standing on a scale and knew your mass and we put a little piece of fuzz in your hand. Is it there? Yeah. Is it affecting your mass? No. Let's jump into a few definitions that have to do with the atom. First is the atomic number. By definition, this is the number of protons. And of course, in a neutral atom, it's also the number of electrons. Isotopes are the same element with a different number of neutrons. And because there's a different number of neutrons, there's a different mass number. Isotopes behave chemically the same. Now, there's also several types of expressions you need to be able to interpret. One looks like this: carbon-14. Obviously, carbon is the atom. 14 is the mass number. You may also see it written like this. C stands for carbon. There are two numbers. 14 is the mass number. 6 is the atomic number. So how do you find the number of neutrons? 14 minus 6. So in this case, there would be 8 neutrons. Let's look a little bit further at isotopes. Notice first that all of them have the same symbol because we're discussing carbon. An isotope has to be the same element, in this case carbon. And notice the mass number is not the same. We have 11, 12, 13, and 14. Now the number of protons is 6 all the time because carbon has 6 protons. If you change the number of protons, we no longer have carbon. In a neutral carbon, there will also be 6 electrons. Now, where did the number of neutrons come from? Well, we know the mass number is protons and neutrons. All the mass is in the nucleus. What's in the nucleus? Protons and neutrons. So in the first case, if you have a mass number of 11, 11 minus 6 is 5. 12 minus 6 is 6, and so on. It's actually important that you understand what an isotope is because that mass on the periodic table is the average atomic mass made up of all of the isotopes. So oxygen's weird mass of 15.999 is because it's an average, but it's not your average math average. You know, in math class, you add them all up and you divide by however many you have. Not the case here. For this, if you look at the formula, it's mass of an isotope times the percent abundance plus mass times percent plus mass times percent and so on. You have to factor in how often it occurs. Now here's an example for you. Boron has two isotopes. Boron 10 has this mass, 10.0129, with a percent abundance of 19.9%. Boron 11 has that mass with a percentage of 80.1%. So you just plug this into the equation. Now I would like to point out one thing. When you multiply by a percent, you need to turn it into a decimal. Make sure you do that or you're going to get a crazy answer. Now let's look at this answer of 10.8110. Does it make sense? Boron 10 occurs about 20% of the time. Boron 11 occurs 80% of the time. Doesn't it make sense that the average mass should be closer to 11 than 10? Let's take a very brief look at the periodic table. We will go into much more detail in Unit 4. First of all, elements are arranged in increasing atomic number. And when we do that, we see this repeating pattern in chemical and physical properties. We say that this is the periodic law because these patterns repeat periodically. Elements in columns have similar properties. And we also call columns families or groups. Now remember, columns go up and down, they hold up porches. Rows go sideways. We sit in the movie theater in rows, not columns. And lastly, recall that we do remove elements 57 through 70 and 89 through 102 and put them at the bottom of the periodic table, truly to make the periodic table smaller to fit on a page. Let's look briefly at the structure of the periodic table. Notice at the top of the columns, you either see the letter A or the letter B. A goes with what we call the main group elements. These are columns 1, 2, 13 through 18. And then the middle of the table has the B, the transition elements. Well, some of these columns have names. 1A are the alkali metals, but that does not include hydrogen because it's not a metal. 2A are the alkaline earth metals. 5A, where the nitrogen is, they are pronounced pnictogen, even though it starts with a P. 6A are the chalcogens, 7A halogens, and 8A noble gases. Now you've been taught that columns 3 through 12 are the transition elements. Well, columns 3 and 12 aren't actually transition elements. By definition, to be a transition element, an atom must form one ion with an incomplete outer set of d electrons. Well, column 3 has 3 valence electrons and they lose them all, so therefore their d orbital is empty. Column 12 makes 2 plus ions. They lose the s electrons before the d electrons, therefore they have a full d orbital. The 4f block is usually lumped in the same family as column 3, believe it or not. And I would like to point out that the number before the A is the number of valence electrons. So column 1A has 1 valence electron. Column 4A has 4. 7A, 7. Let's take a brief look at the 3 types of elements. You will go into more detail in your homework assignments. On the left-hand and middle part of the periodic table, we have the metals. They have luster, which means they are shiny. They are great conductors of heat and electricity, and with the exception of mercury, they are solids. On the other side of the periodic table, on the right-hand side, we have the nonmetals, mostly gases, some are solids, and one is a liquid. Even though hydrogen is not on the right-hand side, it is a nonmetal, and they have basically the opposite properties of all the metals. Now, in between the metals and the nonmetals, along this stair step, we have the metalloids. These have properties of both metals and nonmetals, and they tend to be superconductors.